we it is a simple graph whose vertices can be partitioned such that we have only adjacency if u and v belong to the different partition.
Mm, mm,
Okay,
mm,
so u and v belong to the different partition, so that is fine. And so this is the notation. So suppose we are assuming that there are k parts. Okay,
mm,
so suppose we are assuming that there are k parts,
mm,
and then we use the notation as k of n1 n2 up to nk. So where this n1 n2, these are the number of vertices in each of the partition.
mm,
Okay,
mm, mm.
so this is the number of vertices in each of the partition, and so this is the notation what we use for complete k-partite graph. So means all possible adjacencies are there,
Mm. Okay, but yeah.
right?
But this notation in K complete is the same, is right?
No, no. So the thing is, so for example, uh,
For example, we have the K32. That's the same with.
3 2. This you are saying?
That's the complete graph is the
No, no.
one.
There is a complete bipartite graph, right? So because there are two partitions. So
If
here, for example, you have three
there's
vertices, and
the notation of complete graph, only one. Okay, okay.
right. So complete graph means all possible edges are
K
there. So
K
here,
three. Okay, okay. K3. Okay, fine. Okay.
okay,
Mm.
fine.
Mm, mm, mm,
Right. So a complete k-partite graph. So it is k chromatic, right? So the minimum number of colors is k. Fine.
it's okay.
Right. So next we will consider a special type of complete k-partite graph. So that is called the Turan graph. Okay. The Turan graph, it is denoted by T n comma r. So it is a complete r-partite graph. So this r is represent the number of partition, and this n is the total number of vertices. So with n vertices, whose partite sets differ in size by at most one.
Mm, mm.
Okay. So the difference between the size of the each partition is at most, they vary by at most one. Okay.
Complete. Avatar graph.
Alright. So it is a complete
Complete.
r-partite graph.
Mm. Does it differ? Oh, but not one.
Right.
Yeah,
So it
yeah.
is a r-partite graph where the difference between the
Mm,
set, difference between the size of the vertices,
mm,
vertex set will be at most one. So each partition has certain number of vertices, right? So they
mm.
will differ by at most one.
That's mean wait a minute. That's mean n divide to r. So plus one, plus two, plus three. Yeah. Mm,
Okay.
mm.
So for example, in more general sense, if we want to see it, so these are r partitions, right? So it is k n1
Mm,
n2 up to nr, right?
mm,
And so if I take any ni and nj, so for any i and j between 1 to 1,
mm,
the
mm.
difference will be less than equals to 1. So the difference between them.
Any. Yeah, yeah. Any. Mm,
So ij lies between 1 and r.
mm,
So then the difference between the partition, size of the partition, that is ni and nj, that will be less than equals to 1. So
mm,
either they are same or they are at most different by 1. So for example, so this is a complete three-partite graph, right? K235.
mm,
So it is a complete three-partite graph, and the total number of vertices is 10, right?
mm,
But this is not Turan graph because, for example, the difference between 2 and 5 is more than 1, right? So this is not a Turan graph.
mm,
Okay,
mm. Just, I am concerned that if we given the n,
right.
given n, two question here is the first one. Can we always produce the T
Yes,
graph
yes.
or not? And
For
how
given,
many for the given, how many T for,
right. So you're saying that given n, right? So n is fixed.
hmm,
So n is fixed, there is always unique. So there is only one Turan graph for any given n. And suppose r is fixed, n and r. If you are give me these two quantities, one is n and how many number of partitions we have, then this is unique. There's t n comma r is there is only one.
hmm, hmm. We always can pick up this, right?
Yes, tell.
Given the n, we always pick up n.
Okay, but
Just a question.
no, the r is also you have to give, right? How many partition you are say taking, that also you have to give. So only n will not help us. So the total number of partitions and
For
the number
example,
of partition.
I give randomly n equal to 15.
Okay,
Can we find r?
so n equals to 15. You are saying, right?
Uh,
And what is r?
oh, any uh, we
So
I don't condition on r.
no, but
So,
we
how
need
many
r,
r
right?
we can? The question is if a given n,
Hmm.
so the r should be some specific number, not
Yes, yes.
yeah.
So R, so I need both of them. I need both N
Yeah, yeah,
and R.
yeah. Yeah,
Hmm.
yeah. The thing here is maybe a given n,
Hmm.
the r is fixed. The
Okay.
rule, the cloud form to find the r, not randomly is right. If
Okay.
what I mean is mm, the complete consider is we should give an r and n and r, but
Right.
maybe there are a relation between n and r. So with a specific n, we can uh, we can we can only fix just one r, not many r.
No, no. We can choose many R, right? So because R is the number of partition, so R can vary from 1 to 15. So there are since there are 15 vertices, I can take
Yeah,
any
yeah,
value
yeah,
of R.
yeah, yeah. For example, with this n, can
Hmm.
we find two r?
Mm, no, no. I think the
For
definition of
example, can
hmm.
you give how many r with this n? That's combine the Turan graph.
No, for a Turan graph, the R is unique. So you have to fix one R. So for example, what I'm saying is, so
Mm-mm.
T15 comma 3
Mm.
and suppose T15 comma 4. So
Mm-mm.
these two things are different. So these two things are not same.
Yeah, yeah, yeah. But they exist three fifteen three and three fifteen four.
Yes, both of them exist.
Huh? Exist for example, three fifteen is what?
Yes,
K
T. So T15 comma 3. So this is nothing but K5 comma 5 comma 5, right?
not exactly one. At most one. Okay, at most one.
Right.
I thought that it's exactly one.
No, no. So this is differ by at most one. So it can be
Oh,
equal or 1.
okay, okay. What's the comma for?
Yes. So
Fifteen
that we have
for.
to. So 15 comma 4, right?
Uh,
So right.
maybe we don't find. We cannot find.
Yes, yes, we can find. So the thing is, let me think. So it is 15 divided by 4 is how much? It is 4, 4, 12, 31, 15. Yes. So this is like this. So K 4 comma 4 comma 4 3.
Four, four, four. 3. Oh, so 15 6.
Yes, so 15 6 will be,
Mm.
so 6 3 18. 1 minute, let me think. So 15 divided by, hmm. So if you take,
You know what I mean? I mean it's something, some compound of n and r. We cannot find the k.
no, no, always we can find.
On way. Oh, on way. Yeah, that's
So
that
always we can
is.
find. So for any r in this range, so that is that lies
Mm,
between 1 and n. So
mm,
I can always find t n comma r, that you can find.
mm,
So let me think about this one.
mm,
1 minute. So 15 and 6 is, so 15 divided by 6 is 2 point something, right? So right. So it is 3 comma 3, then 2 comma 2 comma. Is it giving 8 and 6? 1 minute. So right. So one more 3, 6. Right. So this is the thing. So K333 and 222. So this is the Turan
that
graph.
means we can always find
Yes, yes, we can always find.
with any r from 1 to n.
Right, right.
Oh, okay.
So, but once we fix one R and N, then this is
Mm,
unique. So T N comma R
mm,
is unique. So once I fix one R and one N.
mm. Wait me a minute. We
Yes.
can do from n n divide 2.
Right.
No, n2. N in tn2.
Okay.
Tn2. That means we have n divide 2 and n divide 2 plus 1.
Right, right. So that is what.
And we reduce this from this, we reduce n n tn3.
Okay.
Yeah, maybe it will make sense because from two number we reduce three number, and three number we reduce five number by the mean value. Yeah, yeah.
Right.
I think so. Yeah.
So that is the thing. So N
Mm,
and R you have. So this ceiling function you can take N divided by R, and some of them will be N divided by R, this floor function. So that is what we are doing.
mm,
So 15 divided by 6, we have
mm,
3, right? The ceiling of that. The ceiling
mm,
of that will be 3, and the floor of that will be 2. So that's why some 3 and some 2.
mm, 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 yeah, it's okay.
So this is the Turan graph.
Mm,
Right. So the next statement that we are having is, so the next lemma is, so among the simple R-partite graph, so if I consider all simple R-partite graph with n vertices, the Turan graph is the unique graph with most edges. So the Turan graph has the maximum number of edges among all simple R-partite graphs.
is the unit group with the mod is Abatai. Abatai.
Right.
And the number of what is it for each set? It
Mm.
in independent sets. Yeah, yeah.
Okay.
The most yeah.
Right. So how can we do that? So we consider any complete R-partite graph. Okay. So that the complete R-partite graph with set that differ by more than one. So if it is not a Turan graph, so then I will get some of the partition, the size of them differ more than one, right?
Hmm.
So then we can move a single vertex from the larger, the size that has larger number of vertices to a smaller class. So that will eventually increase the total number of edges.
Hmm. Turan Graph. Yes. Mm, This mean 3, 3, 4, 3, 3, 4.
right?
Mm, mm, mm,
So, for example, let us see this how we're
mm,
doing.
mm,
So, this is not the Turan graph, right? Because the difference is more than
mm,
one, right?
mm,
So this is the partition that has large number of vertices, and this is the smallest one, right?
mm,
So I move one vertex, this V, from here to this partition. So this is my new thing, right?
mm,
So then if we calculate the total number of edges, that is nothing but this quantity, right?
mm, mm,
That is 31. But if I calculate the total number of edges here, so it is 33. So it is actually increasing the number of edges.
mm. Wait me a minute. I what it was I consider about
Yes.
the mass be behind this one. We have a sum of summation of the multiplication, and we can from we do
Right.
one term and put in other term.
Right.
Mm, mm, mm. Three, 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 three. Yeah, 31 to 33 was
Yes.
mm, the term 5 reduced to 4.
Right.
Was the term 2 increased to 1.
Yes.
Uh, 10 to 12. 11, 11 to uh, let's see, 6 to 9 is
Right.
increase, but 10 to 12 is also increase, and 15 reduced to 12 is decrease,
Yes.
and degree, increase, decrease, but totally is the increase.
Right. So only the
What
decreasing
is
part is
uh,
15 is decreased to 12,
mm,
but these two are increasing, right?
what is the reason behind? Yeah. Mm.
Right. So the
Maybe,
reason is, so for example, what we are doing is, so this is the single vertex, right? So the
uh,
previously the single this vertex were adjacent to how many edges? So this was adjacent to 1, 2, 3, 4, 5, right?
1, 2, 3, 4, 5.
So degree of 5, V was 5 in the first one, right?
Oh,
So it was adjacent like this and like this, right? So there are degrees 5, right? But
oh,
when I move V to here, what is happening is, so this is remaining intact, but now this is adjacent to 1, 2, 3, 4 more.
ah.
So
The
degree
only
of,
difference here is 5 minus 2,
right. So that
or
is the
minus
two
3.
extra edges what we are having. So previously, since it was here, it was not able to adjacent with any of these four vertices. But once I move it to here, so instead of two vertices, I am now adjacent
Okay,
to four
okay,
vertices.
okay. When we move like that,
Yes.
the number increase is the difference between the last two.
Yes, yes.
Okay, got it. What? That's see what I want to know. Yeah.
Yes, yes. So that is the total number of edges is actually the difference between the two things. So here there are four and here there are two. So that is the increase.
Mm, 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 mm.
Okay.
In the tree, tree. Wait a minute, tree. Yeah, that's it. Yeah. tree. The tree here, the first term tree multiply with tree here. That's a bit. That's if we can divide in two sets.
Right.
Three multiply with two multiply with three,
Yes.
and one multiply with three. Okay, okay. Yeah, yeah. Mm, mm,
Okay.
mm, 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 mm. Yeah. Mm,
So that is why. So if we have the difference between the partition, the size of the
mm,
partition is at most one. So that will have the maximum number of edges.
mm, mm. That's mean when we change, is it the same? Is it right?
You find me?
We can reduce like that.
Yes. Yes.
The the
We
the
can
the
average.
largest to smallest.
Right.
But when the differ is 0 and 1,
Yes.
even though
Then we have to stop there. That is the maximum.
we cannot reduce anymore.
Right. We cannot increase any more edges.
Yeah, yeah. But because it's the same.
Yes. Yes.
Mm,
So for example, here it is 334, right? So here there is no point. Means for example, the almost all of them has difference is one, right? Either one or zero. So there is
mm,
no point of changing the vertex.
mm, mm, mm,
Okay, so here also, if I take one vertex from here and put it in the next one, so still it is 343, right? So that is the same thing, right? So this is same as 343, right?
mm,
So that is no point in doing that.
mm, mm. Yeah. Mm. Got it.
Right. So this is the so what we got is that the Turan graph is the unique graph with the maximum number of edges, right?
Right.
Right. So the next theorem what they're saying is the Turan's theorem. So if I consider all n vertex simple graph with no r plus one click, so there is no r plus one click, then this Turan graph has the maximum number of edges. So
Mm,
r plus one click is the r plus the complete graph, the complete graph on r plus one vertices, right? So if it does not have an r plus one click as a subgraph, then this Turan graph is the graph with maximum number of edges.
mm. Great. That means we delete one node. Uh, the color reduce. Is right.
Right, that is the click. Yes.
Yeah, yeah. No. That one, please. Uh, no. Plus one. That mean plus two.
No, no, no. So r plus two is already contains r plus one, right? So the maximum size of the click is r. That is their same.
Plus two include plus one.
Right.
Plus two. Plus two include plus one.
Yes. So r plus two include r plus one, right? So no r plus one click means we can have the maximum size of the click is up to r. So that is the maximum size we can have.
Oh. Mm-mm. Yeah.
Okay.
Mm. Yeah, yeah.
Right. So this is actually did by induction on the size r. So if G has no r plus one click, so then there exists a r-partite graph H with the same vertex set of G and at least that many edges, right? So since there is no r plus one click, so the number of colors that we are using is r, right?
Mm.
So since R colors we are using, so each color class you can consider as a single partition, right?
Mm. Mm.
So that's why we can consider a R-parted graph each. So this R-parted graph is need not be complete. There can be some missing edges, but actually you can have
Mm.
a R-parted graph, right?
Yeah, yeah. Mm. 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 Right, right. Mm.
So we used induction on R. So if R equals to 1, then
Mm.
we are done, right? So there is only so G and H have no edges because R is 1.
Mm.
And if R is greater than 1, right? So we consider a vertex X that has the maximum degree.
This is in what is it with no and is yeah
Okay.
yeah 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 um mm,
So we consider that this one has the maximum degree, right?
mm,
Then we consider the subgraph. G prime be the subgraph of G that is induced by the neighbors of X.
mm,
So I consider that subgraph that is induced by the neighbor of X.
mm,
Okay.
yeah yeah mm,
So now X is adjacent to every vertex in G prime, right?
mm,
Fine.
yeah yeah yeah
And G has no R plus one click, so the graph G prime has no R click.
because we delete S is right.
Right, right.
Mm,
So we can apply the induction on G prime, and it has a R minus one a parted graph H, such that the neighbor of X with vertex at neighbor of X, right? Such that the number of edges in H prime is greater than the number of edges in G prime.
you can apply on the from did you is minus one purpose uh, uh, what is this?
Yes. Now see the figure; it will be clear.
Is
So this is my whole graph. Okay.
mm,
This is the vertex X with maximum degree,
mm,
and this is the neighboring set. This is G prime,
mm,
right?
yeah.
And this is the remaining part.
Mm. But S have some connect with S minus S is right.
No, no. X is all the
Okay, okay,
neighbors
okay,
of X I have
okay,
taken
okay,
in
okay,
G prime.
okay,
Okay,
okay, okay. Maximum in yeah, okay.
right. So
Mm,
S is the vertex set. Uh, that is the vertex set minus the neighbor of X. That is my S.
mm, mm,
So this is S minus X. This is X, and this is
mm,
the G prime.
mm,
So this you can also say this is actually the neighbor of X,
mm.
right?
Yeah, yeah.
So now by induction hypothesis, I know that for this G prime, I have an H prime that is R minus one part eight, right?
Minus one per time because
Because
it has no arclet.
right, right. H has so G prime has no arc click. That why by induction hypothesis I know that there exists a R minus one part eight graph H prime.
Uh, 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 that's mean they has a minus one clit. That's mean can divide into a minus one per time.
Right.
Mm,
Okay.
mm, mm. Yeah, yeah, yeah. Mm,
So so this has n minus k elements, right? Because the degree we assume to be k. degree is k. So this has k vertices and this has n minus k vertices, right?
mm, mm, mm,
Now, this S is an independent set
mm,
and H is a R-partite, right?
mm,
So if I consider this whole thing, so this
mm,
is now R-partite because it H prime has R minus 1 partitions and this is my new partition.
mm, mm, mm,
Okay.
mm, mm, mm. Yes, mm,
So
mm, mm, mm,
yes, so what I am doing is, so the original graph, so this is my G is my original graph. So in this,
mm,
there can be some edges in between them, right? But
mm,
when I'm constructing edge, so I am only taking those vertices. So there is no edge between them. But
mm,
I'm joining with all possible edges in H prime.
mm. Yeah, yeah, yeah.
Okay,
Mm.
fine.
Yeah, it's okay. It's okay.
Right. So that's why S is an independent set, and that makes H to be R-partite. Now, only thing we have to left to show the number of edges in H is greater than the number of edges in G, right?
Uh,
So by construction, the number of edges in H is nothing but the number of edges in H prime plus this many edges, right?
mm,
So how many edges are there from S to H prime?
mm, mm. Yeah, yeah, the number of S time, the number of vertices time, the number of
Right. So the one H prime has k vertices and S has n minus k. So the number of edges is a k into n minus k, right?
mm,
So,
mm,
so number of edges in G is less than equal to the edges in G prime plus the degree, sum of the degrees in S, right?
mm. Yes. Mm, totally agree.
But I know that the maximum degree is k and number of vertices in S is n minus k, right? So this summation is less than equals to k into n minus k,
Oh, yeah, yeah, yeah. Oh,
right?
mm,
Hence, it follows that this part is less than equals to this, and so the number of edges in G is less than equals to number of edges in H,
mm.
right?
We have J. We have J. We prove that J should less than has the S number of S less than T.
Right,
It in Turan graph is right.
right.
Turan graph. Here the Turan graph is where?
No, the total graph is this is the new graph and this is the construction, new construction. So I have to show that the number of edges in G is less than equals to the number of
That's okay. But the original statement
original statement.
to
Yes.
to
So original
prove
statement what you wanted to show is that the Turan graph has the maximum number of edges, right? For
T and where T and
any simple graph with n vertices that has no r plus one clique, right?
uh,
So what we do is we first prove that the number we from G I can construct a r-partite graph H, right?
mm,
Which has same number of vertices of G but some more edges, right?
mm, mm,
So what I'm doing is, so number of edges in G is less than equals to number of edges in H. So this I wanted to show where H is a r-partite graph,
mm,
right?
mm,
Now by the previous lemma, I know that this is less than equals to number of edges in the Turan graph
mm, mm. Yeah, it's
because
okay.
for any r-partite graph I can compare with the Turan graph. The Turan graph has the maximum number of edges. So I
Mm,
can directly compare with G. So the number of edges in G is always less than equals to the number of edges in the Turan graph. So the Turan graph has the maximum number of edges.
mm,
So this
yeah.
has the maximum number of edges.
Mm, yeah, yeah.
Fine.
Yeah, yeah, it's okay.
Okay, so this was one example we saw. Right. So the next what you have is so if I graph G, if there is no isolated vertex, so we'll say that it is color critical. If and only if I delete one single edge, so it will reduce the chromatic number for every edge.
Mm,
Okay.
mm, mm, mm,
So when you prove that a connected graph is color critical, we can check.
mm,
So we can compare it with any subgraph that is obtained by deleting single edges. So we have to compare the chromatic number
mm,
of the subgraph by deleting a single edge, right?
Cool. C, let E, S, S, yeah. Oh,
Fine.
wait, less than. Less
Right.
than.
So it is critical, right? So
Less than. Oh, less than. Oh, less than. Oh, when we delete S, we should
yes.
use the different color is right.
Okay.
So this increase the color, not decrease the color is right.
No, it is decrease the color, right?
For example, here we delete this S, the one should be three, is right?
Right, right.
So this increase the
So
in,
for example, is
increase
previously
the
how many
kind
colors?
number, the number kind is right.
Yes. So number of colors is actually decreasing, right? So previously we need three colors, right? So one, two, three. So these are the three colors we needed. Now if I delete this edge, we need only two color, right? So this is both we can color with one, and this both we can color with two. So this is just one example, but the thing
Ah,
is,
ah, 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 okay.
we have to verify for every edge. So that is the more strict condition.
Hmm. If this one that's the have no what is it? The connected graph. Yeah,
Okay.
isolated. We don't. They don't have isolated. What is it? Yeah.
Yes, yes. Here we don't have any isolated wire.
Yeah. 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 Yeah.
So the next proposition is
Mm,
so if G is a k critical graph, so here we are considering G as a k critical graph.
mm,
Then for V belongs to the vertex set, there is a proper k coloring of G in which the color on V appears nowhere else, and the other k minus one color appear on the neighbor of
mm,
V.
mm, mm,
And similarly, we have a statement for the edges. So if I choose any particular edge, then every proper k minus one coloring of G minus E gives us the same color at the two endpoint of the edges.
mm, mm.
Okay.
Yeah. Yeah. I think
So
this makes sense. Yeah.
so because it is k critical, if I delete one vertex, then the color will the chromatic number will strictly reduce, right? So that is the reason. So similarly for edge.
Mm, Yeah, it's okay.
Fine. So next one what we have is, so suppose G is a graph with chromatic number strictly greater than k, right? And if you have x and y to be the partition of the vertex set, then this gx and gy, so these are the graphs induced by x
Mm.
and y. So these are k colorable. If these are k colorable, then the edge cut, that is the number of edges that has one endpoint in x and one endpoint is y. So
Mm.
these are at least k edges.
Mm.
So what it is saying, yes, is the statement clear?
Yeah, it's okay. Mm.
So what we have is, so these are the two partitions, right?
Mm.
So since each of them is k colorable, so I can find a k partition, right? I can partition the set x and y into further k parts, x1, x2, xk, and y1, y2, yk, right?
Mm. Mm. Mm.
So these
Mm.
are found by the color classes in the proper k coloring of gx and gy.
Mm.
Fine.
Mm.
So now, if there is no edge between xi and yj, then if I union both of the vertex set, this is an independent set, right? By definition.
Mm.
Okay. So the thing is, we'll have a contradiction. So if I assume that the number of edges in the edge cut is strictly less than k, then actually we can combine the classes of gx and gy to form a proper k coloring of g. So that will be a contradiction because the chromatic number of g is strictly greater than k.
Mm.
Okay.
Yeah.
So the thing is, we create a bipartite graph H with the vertices x1 to xk. So now we are considering these are sets, right, in the original graph. But here we are we are taking the representation of the set. So we are taking single vertex. So the vertices are here capital X1 to capital Xk and Y1 to Yk.
Mm.
So this is clear, right? So we are not taking the whole set. We are taking the set as a single vertex, just for representation.
Mm. Mm.
Fine.
Yeah.
So what we are doing and what
Mm.
is the adjacency relation? So adjacency relation is Xi and Yj. So these are adjacent in G. So these are adjacent in H. If in G there are no edge between the set Xi and Yj, so then I will make adjacent in H.
Mm. Mm. Mm.
Right.
Mm. Yeah.
So now we have assumed that the size of the edge cut is strictly less than k. So if it is less than k, then h has more than k into k minus 1 edges.
Mm.
So what is the reason? So since m vertices can cover at most k edges, right? Because the degree, the edge cut is the maximum degree is k, right?
Mm.
In a
Yeah.
subgraph of k comma k, and the edges of h cannot be covered by k minus 1 vertices.
Mm.
So in this case, this h has a perfect matching.
Mm. Perfect matching. Yeah.
Right. Suppose the perfect matching is m. So now in G, we give the color I to all xi and all of the set yj to which it is matched by m. So we give them the same color.
Mm.
Okay.
Mm. Yeah, it's
And
okay.
since there are no edges between xi and yj, so this we doing for all L. So this produces a proper k coloring of G. So this is a contradiction because the chromatic number is strictly greater than k. Hence, this assumption is false. So the size of the edge cut has to be greater than equals to k.
Mm.
Okay. So this was the statement that if G is a graph with chromatic number at greater than k and xy be partition with gx and gy k colorable, then the h cut has at least k edges. Okay.
mm, mm, mm,
So using that lemma, so we have the following theorem that if
mm,
it is a k
mm,
critical graph, is k minus one h connect.
teman-teman it connected. Every K cut critical. Mm. K minus one eight connected.
Right.
We
So
have
k minus one h
we
connected
have
means you
K
need,
critical. We have K critical. K crit it right?
right.
K critical. K critical. K crit.
So k critical is that coloring condition, right? So if we delete one vertex, it will be strictly less.
Yeah, that's a K critical.
Right. Right.
K
And
crit.
yes, and k minus one edge connected is, so we have to delete at least k minus one edges to make it disconnected, the graph.
Mm.
Okay. So what is happening here is, so if we take any k critical graph G and we consider the minimum edge cut. So these are the two partition of them, and this is the minimum edge cut. Okay. So
Mm.
since G is k critical, by previous lemma, we have that Gx and Gy are k minus one colorable, right?
Mm.
And that will imply that the size of the minimum edge cut is at least k minus one. So
Mm.
that will force that I have to delete at least k minus one edges to
Mm.
make it disconnected. So
Mm.
that's why it is k minus one edge connect.
Mm. Mm. Mm.
Okay.
Yes, yes, it's okay. Mm.
Okay. So maybe today we'll stop here then.
Ah, yeah, yeah.
Okay. Bye.
Right.